So hello guys, my name is Yogesh Matkari. Today we are going to see psychometric processes and its application and its detailed explanation with the example numerical. So moving toward the content. So there are basically 6 to 7 processes are there. Now there are 4 basic processes and other are mixing of this process. So we will see one by one. So first is our sensible heating or a cooling. So sensible heating or cooling is just adding the heat to streams or air without changing its humidity ratio. Basically in this process, humidity remains constant and the temperature increase or decrease depend upon the application. Whether we want to increase the stream temperature or decrease the temperature, that depend upon the application. So here basically we can see in the chart that humidity ratio is constant, and from process 1 to 2 temperature is increasing, showing by the arrow. So that shows the sensible heating or cooling of a stream. So first process, we can see sensible heating. It's just increasing the temperature of a stream without changing its humidity. It's called sensible heating. So psychometric process, in first diagram we can see that the stream is entering from the heating tube, and then it's passing with TD3 temperature, which is coil temperature we can say, and TD2 is a outer temperature, which is outlet temperature of a air. So first temperature is TD1 and outlet temperature is our TD2, and here TD3 we can say it's tube temperature or coil temperature. So now it's simply heating. So we are basically increasing the temperature of a air without increase or changing its humidity. In the chart, we can say the dry bulb temperature of a stream is increasing. First point we are having at TD1 and second is at TD2. This is our sensible heating process, where at the right side we can say that seen that the W1 is equals to W2, which is humidity ratio or specific humidity. Humidity ratio is between lines. So humidity ratio is constant here. W1 is equal to W2. So this is basically sensible heating. The heating of air without any change in its specific humidity is known as sensible heating. Its actual definition of its sensible heating. So now, the heat absorbed by air during sensible heating process may be denoted by a enthalpy difference H2 minus H1. So basically, we can also define it by enthalpy change. So now, heat addition in sensible heating. The amount of heat added during the process may also be obtained from the relation. So here we can see Q is equals to H2 minus H1 plus enthalpy changes addition of heat Q, where we can see uh, H2 is change in enthalpy means Cp delta T. So Cp of air multiplied by temperature difference. Dry bulb temperature here we have taken TD2 minus TD1 plus H1 is equals to W into Cps. Cps means enthalpy of a space and humidity of a water. So here temperature difference TD2 minus TD1. So now after the solving we can get 1.022 TD2 minus TD1. So heat added is Q is equals to 1.022 TD2 minus TD1 kilojoule per kg or watt. So now for a sensible heating, steam or hot water is passed through the heating coil. The heating coil may be electric resistance coil. The sensible heating of moist air can be done at any desired temperature. So what is exactly this point? So air can be heated at any point of the process. Means firstly we can change its humidity also, and then if we want to add the heat, so there also we can add the heat. Now in the solution we get the term CPA plus WCPS is called humid specific heat. It's denoted by combinedly denoted by CPM, and its value is taken as 1.022 kilojoule per kg Kelvin. So now moving towards our second point, which is sensible cooling. Now its process is same as the sensible heating, where heating coil is used, and here we use cooling coil. When air temperature is changed, air temperature, inlet temperature is higher and outlet temperature is lower. It's basically cooling of a coil, cooling of a air with the help of cooling coil. And now in the chart we can see the difference. We can see that the only arrow by we are denoting it sensible heating. In sensible heating, TD2 is greater, and in sensible heating, TD1 is greater than the TD2. Which basic difference between these two processes. Now, sensible cooling is cooling of a air without any change in specific humidity. It's known as a sensible cooling. The heat rejected by a air during sensible cooling may be obtained by enthalpy difference H1 minus H2. Now, here W1 is equals to W2 and specific humidity is constant. Now, dBT reduces from TD1 to TD2 and from enthalpy from Q1 to Q2. The same explanation is given as sensible heating. So now in the note we can see for sensible cooling, the cooling coil may have refrigerant, cooling water, or cooling gas or flowing through it. Means cooling we can do simply by refrigeration cycle on or same as the sensible cooling can be done only up to dew point temperature as shown in figure. This is the important point. Here we can see in the chart cooling can be done till the TDP. It's dew point temperature of a coil. So beyond that, we cannot cool the our stream temperature. So this is important point to note. What if we can heat beyond the TDP? So cooling below this temperature will result in the condensation of a moisture. So their condensation will be done. So this is the formula of sensible heat. Sensible heat MCP delta T. So where rho is a density, who is moisture, or phi is 1.2 kg per meter cube. V is a rate of dry air flowing in a meter cube per minute. Rate of dry flow, volume flow rate is there, and Cp is humid specific heat, which value we have seen that it's 1.022 kilojoule per kg Kelvin. So now substituting all the values, we get sensible heat as 1.2264 into volume flow rate into delta T kilojoule per minute. So solving sensible heat we can get as 0.02044 volume flow rate multiplied by temperature difference. This formula is simple for use in a numerical, so we will use it further. It's actually it's in kilojoule per second because we have taken volume flow rate in meter cube per minute and divided by 60. So here we have to compulsorily take volume flow rate in meter cube per minute. So now moving forward, bypass factor and efficiency of a coil. This is the important point because in numerical sometimes we get the bypass factor and efficiency. So depending upon that, we have to get the outlet temperature. If bypass factor is given and inlet temperature is given, we get the easily outlet temperature or inlet temperature, vice versa. So first of all, we will see that what is a bypass factor. So under the ideal condition, dBT of air leaving the apparatus, which is TD2, should be equal to that of coil temperature, TD3. But because of the inefficiency of the coil, it is not so. So this phenomenon is known as bypass factor. So here we have seen that the air is passing through the machine, and where inside there is heating coil or cooling coil depending upon the application. So let us say there is cooling of a air. Air is passing, which is temperature is TD1, and coil temperature is TD3, and outlet temperature is TD2. Apparently, there should be same temperature of air after the leaving coil, which is equal to coil temperature, which is TD3. But it's not, because there is some loss, and its loss is called as bypass factor, because there is difference between outlet temperature and coil temperature, that is denoted by bypass factor, or we can calculate by bypass factor. So we know that the temperature of the air coming out of the apparatus TD2 will be less than the TD3 in case the coil is heating, and more in case of cooling. So we will see how we can get the bypass factor. Here it is shown by the diagram. Here we can get easily. So let us suppose inlet is 1 kg of air, which is temperature is TD1, and inside there is cooling coil. Now air is passing with 1 minus x kg air passing through the cooling coil, and remaining x kg air passing directly without in contact with the cooling coil. So that remaining air would not be affected by a cooling coil, and just the remaining half air or fraction of air will come into contact with the coil, that will be affected. So after that, the both air will be mixed and come out. So that would be mixing of air, and apparently the temperature would be different than the coil temperature. So that is basically difference. Here we will get three temperature: inlet temperature, outlet temperature, and coil temperature. So we can formulate it. Now the number of it's depend bypass factor is basically depend upon the three factors. First, the number of pin provided in a unit length. It's called as pitch of a cooling coil. Now second point is the number of row in a coil in a direction of a flow. Now third is the velocity of flow of air. These 3 points affect the bypass factor of a coil. Now the bypass factor of a cooling coil decreases with decrease in fin spacing and increase with number of rows. So that point is to be noted. Now we will solve this and get the formula for bypass factor. Here we seen that the fraction of air is passing through the cooling coil, and some fraction of air is passing directly. So x is a fraction of air without contact, and 1 minus x is remaining air which is coming in contact with the coil. So combiningly we will get x cpm td1 plus 1 minus x cpm td3 is equals to 1 into cpm into td2, where we have cpm is equals to specific unit of heat. Now solving, we get x is equal to td3 minus td2 upon td3 minus td1. Now where td3 is a coil temperature, td2 is a outlet temperature, and td1 is inlet temperature. So now here we can see bypass factor is td3 minus td2 upon td3 minus td1. And similarly for a heating coil or cooling coil, we have given it. For the heating coil is Td3 minus Td2 upon Td3 minus Td1 as we solve, and similarly for the cooling coil it's Td2 minus Td3 upon Td1 minus Td3, because inlet temperature or outlet temperature is greater than the cooling coil temperature always in the cooling case. So now moving towards our next topic, which is efficiency of a heating and cooling coil. Now we have seen that the inefficiency of a coil is denoted by bypass factor. So if we minus inefficiency from 1, so that we will get efficiency of a coil, because efficiency and inefficiency are factor one single unit. So now therefore efficiency we can say 1 minus bypass factor, it's directly given by the efficiency. Now, similarly, efficiency of a cooling coil in heating coil we will see. Efficiency of heating coil is denoted nu h, which is TD2 minus TD1 upon TD3 minus TD1, and efficiency of a cooling coil is TD1 minus TD2 upon TD1 minus TD3. So basically, we have to subtract it from 1 bypass factor, so we will get efficiency. Efficiency and bypass factor. This we are calculating in the unit digit or fraction, so its value will be ranges from 0 to 1. So now next topic is humidification and dehumidification. This point we will see in our next video. So thank you for now.